Hi, and welcome to my presentation on optimal control for electromagnetic haptic guidance systems. Pen-based interactive systems that feature haptic guidance support users in a variety of applications such as drawing, sketching, writing, or CAD design. Crucially, such systems aim to strike a balance between giving users a strong sense of control and agency. Previous magnet-based work, such as the band, relies on open-loop control, or like CAD on time-dependent closed-loop control. These strategies force users to adapt to the system rather than the other way around. This gives rise to the question on how we can control haptic feedback systems, especially electromagnet-based, to find a balance between haptic feedback and user autonomy. In our paper, we make two distinct contributions. Our first contribution is a time-independent closed-loop control strategy which enables user autonomy. The second contribution is a prototypical hardware implementation. Let's first discuss our control strategy in more detail. For the control strategy, we assume there is a desired trajectory and pen location. We can discretize the trajectory. With a discretized trajectory, some questions arise that we want to solve with our control. First, what is the closest point on the path? Secondly, what is the desired progress? These two questions are not new and answered in previous work, albeit in a different context. The final question is what haptic force needs to be applied. These questions are answered combined in a model predictive contour control formulation, which is an iterative optimization framework. The third and final question is the main contribution of our paper, therefore let's zoom in on this. In our case, the electromagnet is always attracting the pen. This happens from the center of a permanent magnet embedded in the pen in a straight line to the center of the electromagnet. For the sake of simplicity, we will forget about the Z component of this force. This force is mainly depending on two factors: the distance between the two magnets, as well as the actuation of the electromagnet. This describes the actual force. Calculating the force between two magnets is not straightforward. Crucially, this enables real-time control. For those interested, we derive an analytical equation to do so in our paper. The second element of our cost term is the desired force. This force is in the direction of the desired point on the path. The final cost is the squared difference between the desired and actual force. Now that we discussed our proposed method, let's take a look at the hardware we implemented it on. The system consists of an electromagnet mounted on a biaxial linear stage. The system is agnostic to the tablet that is used to determine the pen location. This can be pressure-based or a tablet with visual feedback. Furthermore, the tool needs to be augmented with a permanent magnet. With our proposed method and prototypical hardware in place, let's evaluate it. We did two experiments. First of all, we tested our system with end users on general accuracy, and secondly, with a set of different users, we compared control strategies. For details of both, please refer to the paper. Let's discuss the end user performance in more detail. We asked 12 participants to draw 6 different shapes with and without haptic feedback. The users received minimal visual support during this task. What we learned from this is that more complex shapes benefit most from haptic feedback. Furthermore, the users are still limited by the physical speed of our system. And finally, the drawings overall become more accurate. Now that we have taken a look at the evaluations, let's discuss potential use cases. As shown here, one of the applications could be to help users with calligraphy. A second application could be to help people with the outlining and inking of complicated sketches. In this case, a dragon is drawn by a novice user without drawing experience. Notice how the system can deal with different line segments and the lifting of the tool, as well as swapping of the tool. These illustrations are drawn with the same system settings. This illustrates how the user is still guided back to the same primitive shapes, yet remains to have creative freedom. Finally, we show a use case with visual support, where a user is manipulating virtual tools in order to support them with the design of a chair. To summarize, we presented a control strategy for haptic feedback, prototypical hardware, and we evaluated our system on users. All blueprints and code are available on our website. Thank you.